In this module, we will discuss the reaction rate. The concept of reaction rate in chemical kinetics refers to the speed at which a reaction proceeds. Chemical kinetics examines reaction rates and the mechanisms behind them. Understanding the concept of the reaction rate is an important first step in the study of chemical kinetics. Reaction rate is similar to speed in everyday terms, such as the speed of a bicycle or a car. In physics, speed is defined as the distance traveled over a certain time interval, typically measured in meters per second or kilometers per hour. If we denote distance by s and time by t, the average speed is given by the change in distance delta s over the change in time delta t. For example, if you drive from Bern to Basel covering approximately 100 km in an hour, you have traveled at an average speed of 100 km per hour. To determine the instantaneous speed at a given moment, we must take the derivative of distance with respect to time, ds over dt, at that specific point in time. In chemical kinetics, instead of speed, we talk about the rate of a reaction. Until later, we constrain our discussion to homogeneous reactions where the reactants are in the same phase. Then we shift our focus from distances to the concentrations of reactants and products. Consider a simple reaction where reactant A transforms into product B. We can measure the reaction rate by observing the decrease in the concentration of reactant A or the increase in the concentration of product B over time. This figure illustrates this concept, showing the concentration of A decreasing over time as it is converted into B. The average reaction rate is determined by the change in concentration delta C over a time interval delta T. To find the instantaneous reaction rate, we look at the derivative of concentration with respect to time, dC over dt at a particular moment. We can measure the rate of a reaction by analyzing the time dependence of reactants or products concentrations. Consider this figure as an example. If we know the concentration of reactant A at the start and after 30 milliseconds, we can calculate the average rate of the reaction as the change in concentration over the change in time. However, this average rate differs from the instantaneous rate, which is determined by the slope of the tangent to the concentration time curve at a specific time point. In this figure, the initial rate at t equal to 0 is represented by the purple tangent, while the rate at 30 milliseconds is shown by the blue tangent. As you can observe, the reaction rate is not constant. For most reactions, it decreases over time. In chemical kinetics, the term reaction rate is defined similarly to the rate of change for other physical quantities. It is defined as the change in concentration of a reactant or product per unit of time. Considering that C is molar concentration with a dimension of amount of substance per volume, the dimension of the reaction rate V is amount of substance per volume per time. Its coherent SI unit is mole times meter in the power of -3 times second in the power of -1. Although mole per liter per second is typically used. The reaction rate can be determined by observing the change in concentration of either the reactants or the products. Let us consider as an example a reaction of A to B. For the reactant A, the derivative of concentration by time is negative, as its concentration decreases over time. For the product B, it is positive as its concentration increases. As one molecule of A reacts to one molecule of B, the time derivative of the concentration of B is the negative of the time derivative of the concentration of A. To account for reactions with complex stoichiometry, we must also consider the stoichiometric coefficients. For instance, in a reaction where one reactant molecule A forms two product molecules B, the change of the product's concentration will be twice as much as the change of the reactant's concentration. These are simple examples illustrating how crucial it is that the reaction rate must be defined in a way that is independent on whether we are considering reactants or products and their stoichiometric coefficients. That can be done by considering the extent of reaction, denoted as Xi. This is a unique independent variable that describes the progress of any chemical reaction, regardless of the number and proportions of reactants or products involved. Formally, the reaction rate is defined as the rate of change in the extent of reaction. Recalling the definition of the extent of reaction, the reaction rate can be also expressed as the rate of change of any reaction participant divided by its stoichiometric number µi. As stoichiometric numbers indicate the proportions of each substance in the balanced chemical equation, the resulting reaction rate is independent of the specific reaction participant considered.